Welcome to this video on carboxylic acids. Well, how do you know if a molecule, upon looking at its structure, can be classified as a carboxylic acid? Well, carboxylic acids have a general structure of R, and R means rest of the molecule. And typically in our world, R can be, but it doesn't have to be, a hydrocarbon group. So in general, carboxylic acids are R, C double bond O, OH. Again, R can be many different combinations of atoms, but what has to be there is this C double bond O, OH. Well, one of the first things we want to do with carboxylic acids is know how to name them. And we already have a well-established set of rules for naming, and we're going to use those rules with some slight modifications. When you identify that, oh, I have a carboxylic acid, you need to focus your attention on the carbonyl C double bond O carbon, because that's going to always be carbon number 1. And then you need to move along the molecule to find the longest continuous chain, starting with the carbonyl carbon. And anything that doesn't fall into the longest continuous chain of carbons will be a substituent. So in this molecule, it's pretty clear, I think. This would be carbon 2, 3, and then we can just go along here to 4. If you went down to 4 to this carbon, that's fine, because these two carbons really are equivalent, to be honest with you. But one of them has to be left out, and the one that is left out has to be in the substituent. And so this is our old friend methyl. Since the carbon of the carbonyl is always 1, there's no need to put that number in the name, because it's understood that, hey, that's always the number 1 carbon. So when naming this molecule, you're going to look at, okay, there's 4 carbons in the longest continuous chain. That's based on butane, but this is not an alkane, it's a carboxylic acid. And so when you name carboxylic acids, they're going to end in oic acid. So it looks like we've got 3-methyl. You don't need 1, because it's always understood this carbon is 1. So it's 3-methyl butanoic acid. So again, that's how we're going to name carboxylic acids. Another thing we're going to do with carboxylic acids and other organic molecules is we've got to be able to predict their properties given some structures. Okay? So one thing about carboxylic acids that make them somewhat unique is that they have both polar and non-polar parts. Now, what do I mean by that? Well, this part of the molecule in a carboxylic acid is definitely polar. It has what we've called before polar bonds, and it is very good at forming hydrogen bonds. And again, that's a very important type of non-covalent interaction, as long as you have hydrogen bond donors and acceptors. And again, we've talked about that before. Now, the R group, on the other hand, the R group is typically a hydrocarbon. So it is going to be nonpolar. And so this is going to play a role in some of the analysis we're about to do with the 2 carboxylic acids shown below, A and B. The 2 questions that I need to know the answer to is which one has a higher boiling point and which one has a higher water solubility. Well, with water solubility, the first question to ask yourself is, what is the ability of a molecule to form hydrogen bonds with water? If you want to be dissolved in water and you're a molecule, you're going to need to form some hydrogen bonds with that, with water. So what we see here when we compare A and B, then the donors and acceptors, the hydrogen bond donors and acceptors that we've gone over in pretty good detail before, is the same for A and B. So if you look at the number of donors for A and B, it's 1. The number of acceptors, remember, acceptors are lone pairs. I'll just put them in real quick. Hey, it's a straight up tie. So the number of acceptors are 4. So D plus A equals 5 for A and B. So hydrogen bonding is not going to allow us to distinguish between the water solubility of A and B. Well, what's the other issue? The other issue is what we have called nonpolar area. How much of the molecule is hydrocarbon? Well, I think you can look at A and B and you compare this R group to this R group. I think we can see B is more nonpolar. Since B is more nonpolar, then the answer to our question is A is more, let's do it this way. A has a higher water solubility because B is more nonpolar. Again, we can make this comparison just based on the structures of A and B. Now, what about boiling point? Well, boiling point, as we've talked about, or maybe we haven't talked about much yet, but we're about to, boiling point depends a lot upon, can the molecule hydrogen bond with itself? If a molecule can hydrogen bond with itself, another copy of itself, then that tends to raise the boiling point. Well, guess what? When you look at A and B, it's a tie. The answer is yes for A and B. So it's another tie. So hydrogen bonding is not really helping us out at all so far in these two issues. So what do we go to next? With boiling point, it is size of the molecule. B is larger, has a greater mass, a molecular weight, a molar mass if you want to say it that way. B is larger than A. So our rule is the larger the molecule, if everything else is equal, the larger the molecule, the greater the boiling point. And so basically B has a higher boiling point. Again, we'll discuss more of this in class, but this kind of gives you a flavor for the kind of analysis we're going to have to do when it comes to answering questions concerning water solubility and boiling point. Well, another major property of carboxylic acids is, hey, the name tells us they are acids. They release, or you want to say donate, that's fine, hydrogen ions when they're placed in water. And so we have this kind of general equilibrium set up. We have a carboxylic acid. Now I'm going to go ahead and draw this bond like that, plus water. And it's going to be an equilibrium because they can go back and forth. Now, if it releases a hydrogen ion, this is the acidic hydrogen. This is the one in a carboxylic acid that will be donated as a hydrogen ion. And it's going to be given to water. So if water picks up a H+, guess what it makes? Oh, it makes a H3O+. It's gained a H+. When water gains a H+, it's H3O now and has to have a positive charge. Plus, what's left over of the carboxylic acid? Well, the hydrogen's gone. That's okay. But if a molecule with no charge loses a H+, then what's left is a negative. So it's R, C double bond O, negative. So what's kind of the take-home message for this? When a carboxylic acid is in the acid form, it is no charge, but when we put a carboxylic acid in water, it can adopt a base form, and it is negatively charged. That's some rules we're going to start establishing. You're going to have to know that carboxylic acids in water can be negatively charged, and carboxylic acids are acids. They have the ability in water to donate or release a hydrogen ion, which is an H+. Okay? All right. In terms of nomenclature we've used before, the H3O+ is going to be called the conjugate acid. And the what's left over here on the carboxylic acid is going to be called the conjugate base, because now this form of the carboxylic acid is a base. It can accept the hydrogen ion from H3O+. So that makes H3O+ an acid. So a base, remember, accepts a hydrogen ion in water. So again, this is going to be very important to the properties of carboxylic acids. Now the last thing I want to touch on in preparation for class on this topic is the ability of carboxylic acids. So let me add acid here. Carboxylic acid plus an alcohol can make an ester. And esters are very important molecules. We've kind of touched on them before, I believe. And ester is, well, I've already drawn kind of the, well, let me give you the general structure of an ester. It is R, again, that's general, C double bond O, O, R. So this is a very important reaction. Carboxylic acids plus alcohols make esters, and it releases a molecule of water. And esters play a very important role in many different things. Also, if you start with an ester, and you treat it with water, then you can break up that ester back to the original carboxylic acid and alcohol. So one of the things that I will be asking you to do is to start with an ester and say that it undergoes hydrolysis. And hydrolysis means to break with water. Hydrolysis means to break with water. Let me move this down a little bit. So what we're going to do is we're going to add water to this. It's still in equilibrium, and then we're going to want to know what's formed in these two boxes here. In one of these boxes has to be a carboxylic acid, and in the other box there has to be an alcohol. Now, how do we know what we make in terms of a carboxylic acid and an alcohol? Well, if you're given the original structure of the ester, we can figure this out. Okay? Now, just for emphasis, this requires an acid catalyst, usually some hydrogen ions. So look out for that as well. But how do you know which carboxylic acid and which alcohol was used to make a given ester? Well, here we go. Locate the ester part of the molecule, and this is the ester part of the molecule. Okay? You're going to ultimately, when you hydrolyze an ester, you break this bond. And when you break that bond, let's just chop it with this arrow. We're going to break the bond. Then water comes in and adds to the two fragments to make the carboxylic acid and the alcohol. So if we say this is water, I'm drawing it this way on purpose. HOH, H2O. I'm drawing it like this. Well, if this bond's breaking, then this C double bond O needs to pick up another bond to be happy. Oh, well, look. That OH can be added to that carbonyl. Wait a minute, that will give us a carboxylic acid. That's what we needed. Okay? And this oxygen, if it picks up a hydrogen, then it will make an alcohol. And then this bond on water will also break, and then we'll have what we need. So what we get is CH3, CH2, C double bond O, OH. So that can be in this box here. This is the carboxylic acid. And then we will also get this alcohol. So basically you can draw the structure, if given a structure of an ester, and again this will go in this one. This is the carboxylic acid, and this is the alcohol. If given the structure of an ester, and I say it undergoes hydrolysis, you can draw the structures or give the name possibly of the carboxylic acid and alcohol that was used to make it. Also in class, we'll go the other direction. I'll give you a carboxylic acid and an alcohol, and we'll make an ester from that. Alright, hope this video was useful in preparation of class on this topic.